Hi everyone, today I want to show you how you can compute a linear approximation using differentials. So today we're going to compute the value of square root of 16.2, okay? So now you can imagine that this value will be very close to 4, but it's not going to be exactly 4 because we have this decimal point right there, okay? So now to use differentials, well, first I want to give you a picture of how differentials can be combined with exact values because, well, a differential is not exactly a very particular or well-defined value, I would say. Okay, so I want to show you how you can use differentials in a geometric way, how you can use differentials to compute this value. Okay, so the square root function will look something like this. Okay, now I'm going to define 4 points. Okay, we're going to have an x point, which is going to be here. We don't really care about what value x takes. We're just going to say that this is x. We're going to say that this is x plus dx, okay? And we're going to say that in here, it would be kind of like here. This would be y, okay? And over here, very close to y, we would have y plus dy, okay? These are going to be the 4 values that we're going to play with. So I want to ask you the following. So if you evaluate y at x, well, you're going to get a point that is over here, okay? Now, if you remember, differentials are what we call infinitesimals. An infinitesimal is a very small value. So when we say the differential of x, we're referring to a very small value of x, okay? So we could say that although this function doesn't look like a straight line, as it should if you zoom in a lot, so we're going to say that dx is a very small value. So basically, this is going to be a very small portion of the square root function, okay? And in real life, it should look like a straight line because you're zooming in a lot. But in this case, well, it's kind of curvy. But that doesn't matter, okay? I just want to show you the geometric picture first. So if you evaluate y at x, you're going to get this point here. And if you want to find how much y changes when your input, which let's say 16, you have your input and you add to your input a very small value of x, which is going to be dx. And let's say dx would be this 0.2 quantity over here, okay? So what happens with y as you add 2x, that would be 216, as you add dx, meaning what happens at 16 is added to 0.2, okay? What happens with y, and well, the result is gonna be y plus dy, okay? So what I wanna show you is that, okay, so let me first put a point over here, which would be kind of something here. Okay, so dx is going to be, of course, this distance over here, and dy, well, is going to be the rise, okay? Remember, this is kind of what we have, okay? It would be something like that, okay? This little chunk over here is going to be dy, and this portion over here is going to be dx, okay? If you want to find how much this function, this function is going to be square root x, so if you want to find how much x plus a very small value, that is x plus dx, how much that is, if you evaluate it at y, well, you're gonna have to find y plus dy, okay? I hope I'm just trying to give you some intuition into the geometric picture of using differentials to compute linear approximations, okay? So now I'm gonna jump to the algebra, which hopefully makes more sense. So the first thing that we're gonna do is the following. So I'm gonna change to black. Now we're gonna define a function, which is gonna be y is equal to square root x, okay? Because, well, you can see that we're using the square root function, we're using a radical, and one of the best ways in which we can represent this value is by using square root x as our function, okay? So now we want to find y plus dy, okay? Now we know that y plus dy would be the same as the function that is y evaluated at x plus dx, okay? Now we know y would be square root x, so we can write square root x, and inside the radical, well, we're going to have not only x, but x plus dx, okay? So we're going to have something like this. Y plus dy is going to be our function y evaluated with a bit more x, or with a greater yet small addition to x, okay? I hope this makes sense what I'm saying right now. So this is the first equation that we have. And we need to find y and dy, okay? And that's how we're going to compute this value over here. So if we say that 16.2 is equal to x plus dx, which is what we're implying with this equation, well, we can find very easily dx, okay? So x plus dx is going to be equal to 16.2, okay? And as I said before, we want to have, maybe I didn't say it so explicitly, but I hope that you can infer that. if we're using a linear approximation, we need a base point that we will use to approximate another point. In this case, the base point that we're going to use is going to be x equals 16, okay? Because 16, well, gives us a very exact value for y, okay? We know square root 16 is 4, okay? So we're going to say that x is equal to 4, which means that y is equal to I'm sorry, this would be the other way around. I just switched the, the value, so it would be x equals 16, and y is equal to 4, okay? Now, if x is equal to 16, then we have 16 plus the differential of x is going to be equal to 16.2, okay? And now you can just subtract 16 from both sides, and you get that the differential of x is going to be 16 minus 16.2 minus 16, which I'm just going to write it as 0.2, okay? I'm not going to write the entire subtraction. So this is the value for the x, okay? And now we already have the right-hand side of this equation, okay? We already have square root of dx 0.2 plus 16, okay, which is the value that we want. And now we just simply need to find y plus dy and see how much that is. So we already know y, which is great, and the only thing that we need to do is to find dy, okay? And here's where we're gonna have to use a bit of calculus. So we know that the differential of y is gonna be equal to f prime. I'm gonna write the entire thing, so it's gonna be f prime of x times the differential of x, okay? Now we know f is equal to y, so we have that the differential of y is going to be y prime, which is square root x. Now I hope that you probably already know that the derivative of this function is just simply 1 over square root, and I'm actually gonna write the 2. I'm actually gonna write the entire thing together, so this is gonna be dx divided by 2 square root x, okay? So this is the differential of y. The derivative of the square root x is going to be 1 over 2 square root x, and then you multiply by the differential of x, and you can just simply put together those two numbers, and you get this fraction, okay? So this is going to be the differential of y, and this is great because we know how much x is. We know it's going to be 16, and we know how much dx is, okay? So we know this is going to be 0.2 as dx, which I'm going to write as 0.2. That would be the same as 2 over 10, which is 1/5. So I'm going to say this is 1 over 5 times 1 over 2 square root x. We know x equals 16, so that would be 2 times 4. And that's going to be 1 over 8, okay? So this would be 1 over 8. And, well, this is pretty simple. You just get that. This is 1 over 40, okay? And this is the value for dy. And now it's pretty easy what you need to do. You just simply have to say that, well, we know this is going to be the square root of 16.2. And we can just simply plug the values for y and dy. We know y, once again, it's going to be equal to 4. So we have 4 plus dy, which we know is going to be 1 over 40, okay? Which is going to be 1 over 40, okay? And this, it will be equal to 4.025, okay? Now, you got to be careful with these signs. Of course, I'm using equals here, but it's not very accurate to do that. In fact, mathematically, it's not correct to use equal signs here. So really, you want to say that this is just approximately, okay? Remember, we're using a linear approximation. So, well, you want to be careful with whatever you're, with the signs that you use, okay? Because the exact value of this is square root, well, it's not going to be 4.025, but it's going to be very close, okay? So that's the entire thing. That is how you can use differentials to compute linear approximations, okay? You have, you just simply need to find, first you want to write this equation, so you know what values you need to find. Remember, whatever x plus dx is going to be the input for your function. Usually it's going to be an input that is kind of uncomfortable to deal with. It's not very easy to compute the square root of 16.2 in a, well, just with pen and paper, okay? It's not very easy. So usually x plus dx will be that annoying and, uncomfortable input. And you can just simply, use x plus dx as your input, and then understand that that will be equal to y plus dy, okay? And you can understand that by seeing the geometric picture, okay, which is kind of hard to explain, You need to understand that dx is a very small number, and here we're zooming in to the graph of square root x, okay? So yeah, that's like an extra remark. So yeah, that's been the entire thing now. I hope that you enjoyed this video, you learned something, and see you in the following one. Bye.